Right, so in our last unit, we talked about naming chemicals, naming ionic compounds. And so in this new chapter, we're going to start looking at how do chemical changes get represented, and how do these chemicals bond together to form new things, right? And we're going to talk about something called chemical reactions. So at its very basis, chemical reactions are kind of the foundation for everything really on the earth, right? We don't survive without different chemical reactions taking place, right? Reactions as simple as water forming, right? That's a very, very essential chemical reaction for us. And then we have chemical reactions taking place in our body all the time. So let's talk a little bit about what is a chemical reaction, right? What are they? Chemical reactions are any sort of change that happens in which we take one or more substance, and we change them into one or more different substances. We make something new from it. Okay, so a chemical reaction really comes from a chemical change, right? If a chemical change takes place, that means something new is forming. I wanted to kind of counteract that with talking about a physical change. A physical change is when we just change the state of a substance. So if something goes from solid to liquid, that's just considered a physical change, right? But if it becomes something new, if it has a new identity, then it's a chemical change, and therefore a chemical reaction has happened. So a chemical reaction is made up of two distinct parts. The first part of the chemical reaction is called the reactants. The second part of the chemical reaction is called a product. So reactants are what goes in to a chemical reaction. So whatever you're starting with, or the original substances, those are called reactants. Okay, whatever I'm starting with is called the reactant, and then whatever is made is called the products. All right, so if a chemical reaction is when we turn one or more substances into something different, this would then be my reactants, and this would be my products, right? I start with one thing, and I end up with something different. So in order for something different to happen, I want to kind of take a little side note here. In order for something different to happen, okay, let's write out just a basic chemical reaction. Some compound A plus some compound B yields some compound A, B, right? They bond together. So in order for a chemical reaction to take place, the molecules or the atoms in compound A now break apart from one another and start bonding with the atoms from compound B to form a new type of compound, AB. Okay, so it might look like this. We might have lithium atoms and chlorine atoms, and they might combine to form a new compound called lithium chloride, right? And you guys know how to name that, lithium chloride. But what happened here is I took a certain amount of lithium atoms and a certain amount of chloride atoms, and I stuck them together. My lithium atoms started breaking apart from one another and started bonding with individual chlorine atoms, and so that's what formed lithium chloride. Okay, so at its very basis, a chemical reaction involves breaking the bonds of our individual reactants and forming new bonds to form a product, right? So they kind of get away from themselves and they go bond with something new that forms a product. Okay, so I want to kind of talk about that just a little bit. So how do we know if a chemical reaction has taken place, right? We said it happens with a chemical change. Something new is formed. So there are some ways that we can determine if a chemical reaction has taken place. So we know that chemical reactions are a formation of something new, but sometimes we might not be able to see that, right? We might not be able to see a new compound being formed. Let's say we put together two compounds that are in liquid form and they mix, right? But they stay a liquid. Then it's hard to tell if a reaction has really taken place, right? If we can't visually see something new form, it might be hard to tell. So there's a couple ways we can see if a reaction has taken place. The first of which is a color change. So if I put together two objects that are the same color, right? If my reactants are both the same color, and yet after the reaction is over, the product is a different color, that has to tell you that there's something new that has formed, right? My compounds have been transformed. They've formed something new. So a color change is a good indicator. If there is a gas that is produced, that's a good indicator for us that a chemical reaction has taken place. So if I mix together two liquids and bubbles start forming, right? Bubbles are an indicator that a gas is present. So if it's not boiling and bubbles are present, that tells us that there's a gas that's being produced and those gas particles are trying to get their way to the surface. If my reaction changes heat or energy, so if my two substances that are reacting become hot or become cold, that's a good indicator that a chemical reaction has taken place. So if they react and they release heat or they release light, that's a good indicator that something's taken place. So there's some good examples of this version of chemical reactions in like ice packs. Okay, have you seen ice packs that are portable? And to get the ice pack to turn cold, you have to kind of break this piece in the middle. You have to snap it. That's basically releasing a chemical so that a reaction can take place and get cold, right? It's going to absorb that heat, so it's becoming cold. The same things work with like hot hands that you can use when it's really cold outside. You have to shake that packet, and so that tells you that shaking, that's causing or starting a chemical reaction, and the heat that's given off is an indicator for us that a reaction is happening, right? It's not just magic that it gets hot, right? These whatever two substances or reactants that are in there, they are reacting and it's causing that heat to be let off. Another one is glow sticks. Right? When you want to get a glow stick started, what do you have to do? You have to snap it, right? That snapping is breaking interior capsules in that glow stick and causing or allowing these two substances to mix and start the chemical reaction that causes the glow. So these things are more common than what you really might think. Okay, the last indicator that a chemical reaction has taken place is the formation of what's called a precipitate. Okay, the precipitate is a solid that appears in a chemical reaction. So let's say I mix two liquids together and all of a sudden a solid is formed, right? There's a chunk of something in that container. That's got to tell us that a chemical reaction has taken place. Okay, so those are just some indicators. You might even write it up here. These are chemical reaction indicators. Oops, I can't spell. Okay, indicators, that's indicating to us if a reaction has taken place or not. Okay, so what are some characteristics of chemical reactions? All right, and let's go back just a little bit. It's here. This says chemical equations. Characteristics of chemical equations. So the way that we write out a chemical reaction is through something called a chemical equation, and I wrote one out earlier. A chemical equation is when we say some compound A plus some compound B yields this compound AB, right? This is a chemical equation that is describing the chemical reaction of this compound plus this compound produces this compound, right? Another chemical reaction might be, or a chemical equation is that same thing, right? Lithium plus chloride yields lithium chloride, right? This is a chemical reaction, but the way we write it, 1 plus 2 yields this, is the chemical equation. Okay, so a chemical equation is just a way to show a chemical reaction. So when we write out a chemical equation, we have to know that we write out everything we know about the reaction. We have to put in all the reactants and all the products. For right now, we're not really going to be worried about writing out chemical equations, but what we are going to be worried about is looking at the law of conservation of mass in a chemical equation. Okay. The law of conservation of mass says that atoms are not created or destroyed during ordinary chemical reactions. Atoms are not created or destroyed during ordinary chemical reactions. That might be something we've heard before. Okay, atoms are not created or destroyed during ordinary chemical reactions. That one is really important. Okay, so in a chemical equation, we cannot bring in atoms out of nowhere, and we cannot lose atoms out of nowhere, right? What that means is that if we said our equation was lithium plus chloride equals just lithium, this wouldn't be complete because chloride is not listed on our product side. So that cannot be true, right? That cannot be the case. We have to have every reactant that's listed here has to also be on the product side. The thing that will be different is that they will not be exactly the same as they were on the reactant side. Lithium is by itself as a reactant, chlorine is by itself, but when they form something new, now they are bonded together, so that's a whole new compound. So between the reactant side and the product side, we will see these atoms change places. So even if they're changing places, we have to know that the number of atoms of each element have to be the same on each side. So if we have one lithium on this side of the arrow, we need to have a lithium on this side. If we have one chloride over here, we have to have a chlorine over here. Okay, and so that's what we're going to start looking at as we deal with the law of conservation of mass. All right, so now that we know the basics about a chemical equation, we're going to start looking at some of the symbols that are used in a chemical equation. The first of which are the three states of matter: solid, liquid, and gas. When you see a chemical reaction or a chemical equation written like this, Li plus Cl yields whatever, these single letters listed to the right of that compound or that element give us the state of matter. So this is telling us that lithium in a gas form is combined with chlorine in a gas form, and it yields lithium chloride, which is a solid. Okay? There's not a whole lot else that we need to know about these abbreviations right now. As you get into more chemistry, you will use those and be able to decipher them a little bit more. But for right now, I just want you to know what they are and what they mean. Okay? They don't right now affect how we solve chemical equations, but they just give us a little more information about it. The one that's a little bit new to us is the one that says AQ, and it means aqueous. And aqueous just means that that compound has been dissolved in water. Okay, so I want to even write in further here that it's been dissolved in water. So if you see something, usually it's, I don't know, maybe an acid, HNO3, and it'll say AQ. That just means that that substance has been dissolved in water. Okay. The next one is the arrow right here, and we use the arrow similarly to an equal sign, but what the arrow sign really means is that it yields. Okay, yields means the same as produces. Okay, so I might even write that up here. So when we see, I'm going to go back to this one we've been using, Li plus Cl, those are our reactants. They produce or they yield the product lithium chloride. Okay, so these again are the reactants, and this is the product. The last thing is a double arrow. All of this tells us is that our reaction might be reversible. So if we go from lithium and chloride to lithium chloride, that compound could break down again and form those individual ions again. Okay, so here's an example of a chemical equation for the chemical reaction of this potassium chlorate breaking down. Okay, it breaks down and produces a smaller molecule, potassium chloride, and oxygen gas. These indicate here that it's a solid, and a gas. And then in the next couple days, we're going to be looking at what these numbers here in front of that compound mean, but it allows us to balance the reaction. Another thing I want you to look at with our law of conservation of mass is that we have potassium on this side, right? Potassium and potassium, chlorine, chlorine, oxygen, and oxygen. So you notice that every atom that's present on the reactant side is also present on the product side. All right, so going from that chemical reaction and those symbols, we are going to talk about those numbers that go in front of the formulas, and those are called coefficients. Just like you have a coefficient in math, right? 2x plus 4x equals whatever. These are considered coefficients. They go in front of the unknown, or they go in front of the variable. The same thing works here. So a coefficient in a chemical equation allows us to tell that we need more than one molecule. Okay, so if we need more than one of that compound to help satisfy the law of conservation of mass, that allows us to show that. So here's an example of what I'm talking about. If I have in my chemical reaction something that says 2H2O, this 2 right in front means that I have 2 of that entire molecule. So I have 2 of the H2O molecules. So if I'm looking at individual atoms, I have 4 total hydrogen atoms. 2 hydrogen atoms per molecule times 2 molecules. Right? 2 hydrogen atoms per molecule times 2 total molecules. So that would give us 4 total hydrogen atoms. Oxygen is the same way. We have 1 oxygen atom per molecule times 2 molecules, which is 2 total oxygen atoms. Okay. So if I look at this chemical equation right down below us here, we see that we have 1 molecule of C10H8, because when there's no coefficient listed here, that means we assume there's a 1, right? When there's no coefficient that is listed, we assume it's a 1. Then we move over to the O2 molecule. There are 12 oxygen molecules. We move over to the CO2 molecule that has 10 CO2 molecules, and we have 4 water or H2O molecules in this reaction. So these coefficients are put in place to help us satisfy the law of the conservation of mass, and that's what we're going to look at next time, but I want to show you just a couple little review things here. So let's think first. These are the reactants, and this whole set over here are called the products. Okay. If I'm counting the individual atoms to satisfy the law of conservation of mass, we have 10 carbon atoms. 1 carbon atom per molecule times 10 is 10 carbon. Okay, I have 8 hydrogen atoms on the reactant side. 2 times 4 gives me 8 hydrogen atoms on the right side as well. And then if I look at oxygen, I have 2 oxygen atoms per molecule times 12, which is 24. And if I look over here, I've got 1 oxygen times 4, which is 4, plus 2 oxygen atoms times 10, which is 20. So over here, I have 24 oxygen atoms as well. So that does satisfy the law of conservation of mass. That is why those coefficients are in place, right? Remembering that there is a 1 right there. We will get to that part of it and adding the coefficients in the next class, but I wanted you to be able to see why those numbers are there and why they are important, right? They help us satisfy the law of conservation of mass. But we're going to get to that before too long.